All right. So last class, we were doing this super fun problem where I asked you to find basically everything that was in solution at the end. So the amount of both reactants and both products, and we came up with a little table like so to talk about grams of everything that was remaining, and we decided that the limiting reactant should be completely used up. So by the fact it was a limiting reagent, we said there were 0 grams left. Any questions on that one? Okay, so every once in a while a problem like that appears on an exam, so make sure you're ready to do a problem like that. All right, so moving on to, yes?
I have a question for, why do we have 2 milligrams of silver and not zinc?
So,
Why do we first have 2 milligrams for silver? You said.
well, here we wanted to find the grams of everything. When we started, way back when, I asked you to find the grams of silver. It was just, I picked that one. I could have picked the other product as well. So my recommendation when you get this problem, if you get this problem, and I say, hey, tell me about everything that's left over, start with one of your 2 products. And then once you get the limiting reactant, you're going to use that limiting reactant to find everything else. All right, so good question. Any other questions? Okay, so next up, we're going to talk about percent yield. So here's an example of calculations where you would produce 100 grams of product, but at the end of your experiment you only had 80 grams. So this is very common, especially in organic chemistry. So many of you are going on to organic. They do not have 100% yield. That is not how those chemical reactions work. And they are published with their percent yield. And some yields are only like 60%. You're only going to get 60% of what you thought you were going to get. So what we always do is put our actual yield, this is the yield that was in the lab, divided by the theoretical yield. That's the yield that you calculate. So thus far we've been calculating how much we should get of everything. That is the theoretical yield. That is like your boss saying, hey, you're going to make $100 in tips tonight. And you're like, please, I know I'm not going to make that much. That is like in my dreams. I'll make $20 in tips now. Whatever you actually make is right up on the top. So the actual yield either has to be given to you in the problem or you find it yourself in the lab. This actual yield, again, it is a lab value, so either you weighed it out yourself or the problem has to give it to you. Theoretical yield will always be a calculated value. So you take what you got divided by what you should have gotten times 100, and that's how we're going to get our percent yield. So questions so far on the percent yield? All right, so just a little bit more about that percent yield. So again, the theoretical yield is the amount of product that is calculated. Whenever you do a gram to gram conversion, that is your theoretical yield. It is how much you should make in theory. The percent yield, that is the percent of the theoretical yield you actually obtained. What percent of your calculation did you really get in the lab? So that's what we're doing with calculating our percent yield. So questions so far on the percent yield? All right, so here's our problem. We're looking at adipic acid, and it's used to produce nylon. The acid can be made commercially by controlled reaction between cyclohexane and oxygen gas, which will also produce water vapor. So we're going to carry this reaction out with 25 grams of cyclohexane and excess oxygen, all the oxygen we want in the world. And first we will find the theoretical yield, and then we will do our percent yield. But let's go ahead and do our chemical reaction first. All right, so we're looking to make adipic acid. And we know we are also going to produce water vapor. So these are going to be our 2 products. And what are our 2 reactants? I have cyclohexane and oxygen gas. Excellent. All right, so our reactants are going to be our cyclohexane, C6H12 plus our oxygen gas. Do I just write oxygen like that?
O2.
O2, thank you, it is a diatomic. And now we are going to move on to do our product. So H2C6 H8O4 plus H2O like so. So any questions on where I got the reactants or the product, or how I determined which one was a reactant and which one was a product? So this is a form of a combustion reaction, but for our purposes, I just want you to think of this as how we're producing this adipic acid. But to balance it, we have carbon, hydrogen, and oxygen on both sides. On the left-hand side, right over here, how many carbons do we have? I think I heard some murmurs of 6. Do y'all agree? All right, 6. And how about hydrogens? 12. Excellent. And oxygen? 2. All right, now we're going to move on to the right-hand side. How many carbons? 6. All right, how many hydrogens total?
12.
So, yes, we're at 12. And how many oxygens? 5. Y'all agree on 5? Okay. So this one's almost balanced. Carbon's looking good, hydrogen's looking good. But we have that pesky problem with the oxygen where we have 5 on the right, and 5 is an odd number. Do y'all remember the rule that we learned when we have an odd number of oxygens? Double it, yes. All right, so I'm going to rewrite this, and I'm going to double everything. I'm going to say 2 of our cyclohexane. Hey, did you have a question?
What is oxygen to reach equilibrium? We double up the amount.
So we are doubling everything because we found an odd number of oxygens on the right.
Oh, an odd number on the right.
Yes. All right. So now we have 2O2 plus 2 of our adipic acid plus 2 of our waters. And now I'm going to rewrite our lists. I'm going to say we have 12 carbon, 24 hydrogen, 4 oxygens, 12 carbons, 24 hydrogens, and 10 oxygens. All right, so any questions on how I got that second part there, the new chemical reaction and the new counts underneath? Or any questions about why we decided to double everything? So this is our reaction. Carbon still looks good, hydrogen still looks good, and oxygen still has problems. So if I was to replace the 2 in front of O2, what would we replace it with? I think I heard a 5 out there somewhere. All right, so instead of a 2, if I made this 5, how many oxygen do we now have? 10. All right. So any questions about how we wrote or balanced this equation? All right, so just to make it neater, I'm going to go ahead and just copy everything down one more time. So 2 of our cyclohexane, 5 of our O2, going on to 2 of the adipic acid, plus 2 H2O, and this is our final equation right here. Any questions on how we got this one? All right. So the first thing is that we are going to carry this out with 25 grams of cyclohexane. All right, so we're carrying out the reaction with 25 grams of cyclohexane and excess oxygen. We want to know what our theoretical yield is, and what we're talking about here is the adipic acid. So what I want y'all to do is a gram-to-gram conversion, just like we've done in the past. You're going to start with the 25 grams of cyclohexane, and you are going to end up in grams of adipic acid. So give this a try again, gram-to-gram conversions, just like we've done before, and then we will do the percent yield together. So feel free to work with your neighbors, and let me know if you have any questions. All right, so 25 grams of our cyclohexane. All right, what was our next step from here? Yes, we need to get into moles using the molar mass. Excellent. So grams of cyclohexane for every 1 mole of cyclohexane like so. And how many grams did you get for your molar mass?
84.
All right, so 84 point, what was it?
I got 84.096.
096. Did everybody get something similar? Yes, no, maybe? Yes, no? Okay, let's go ahead and calculate it together. All right, so we have 6 times our carbon plus 12 times our hydrogen, and I'm getting 84.156, something similar to that? Okay, I think I probably just heard you wrong. Did everybody else get something similar?
Yeah.
Yes? Okay. All right, so we were in moles, and next up we're going to use our mole ratio to go from moles of our cyclohexane to moles of our adipic acid. All right, and it looks like for every 2 moles of cyclohexane, we have 2 moles of adipic acid. And so what I told you last time is I do want you to put these 2's in here. And for those of you whose brains are screaming, no, it's not 2 to 2, it's 1 to 1, just go ahead and draw a line through those. But do put those 2's in there so that I know that you looked at your balanced equation. Any questions about putting those 2's in there instead of a 1 to 1? I know mathematically your math teachers would tell you, hey, they're the same, and mathematically they are. But to me, when I see those 2's, I'm like, oh, they looked at their balanced chemical equation. When I see the 1's, I was like, did they really remember their balanced equation? So please do put the 2's in, and then feel free to draw a line through them. If that 2 to 2 screams at you, I'm a 1 to 1. All right. So then our very last step is going from moles to grams. So for every 1 mole of adipic acid, how many grams? What was your molar mass?
146.14.
All right, 146.14 grams. Did everybody get something similar for your molar mass? All right, any questions on how we set this one up? Just to kind of review for a moment. Does everyone see how it still fits what we did? I think this was a couple classes ago, grams to moles, moles to moles, and moles to grams. I told you I would torture you with that until it sunk in. All right. So what did y'all get for your final grams of adipic acid?
43.4.
All right, did I hear 43.4 like so?
Yes.
Yes, okay. This sounds like most of you got something similar. All right, any questions on how we're doing gram to gram conversions? All right, so again, I will tell you, you have a 100% chance of seeing a gram to gram conversion on your next exam. So make sure, if nothing else, when you walk into exam 2, you're like, I know my gram to gram conversions. All right, so now what I'm going to tell you is this value right here, because it is a calculated value, is our theoretical yield. What I didn't tell you before is that every time you calculate one of these values, it is always a theoretical yield. It is how much you should be able to produce in a perfect world if you were a perfect human and you had perfect supplies. And so although you are a perfect human, you don't have perfect supplies. So in other words, the theoretical yield is never the yield you're actually going to get in the lab. It is only how much in theory, and it is the maximum possible yield. So every once in a while in lab, someone's like, ooh, look, I got over 100% yield. I am awesome. I created matter. And the truth is, it's just a little wet. It's attracted some water from the environment. But this is a theoretical yield, so it is the maximum you could possibly get unless you got some water in there or something else random happened. All right, so from here we're going to do our percent yield. All right, so percent yield will always be the actual yield. And this one will be measured in the lab or given in the problem. And that will be divided by the theoretical will be calculated, and all of that will be times 100. So again, on the top, the actual yield needs to either be measured in the lab or it will be given. There's nothing you can calculate. And on the bottom is the theoretical, and that is the one that will be calculated. So questions so far about that percent yield? So that said, let me grab that actual yield from the problem. All right, so it says if you actually obtained 33.5 grams of adipic acid, what would be your percent yield? So I'm going to put that 33.5 in the top, divided by what we thought we were going to get, 43.4. And we're going to multiply times 100%. Notice the grams will cancel out. Our final unit will just be a percent. So 33.5 divided by 43.4 times 100. And those of you calculating along, did you get something like a 77.2%? Yes, excellent. All right, so any questions on how we got our percent yield, where the numbers will come from, the units, or anything else here? So I definitely want you to be able to calculate a percent yield. So questions on anything here with this problem? All right, if you're thinking, oh, my fingers are so tired from the calculator, take a big break from calculations. It is your lucky day. We're going to start talking about solutions next. So solutions are the things that we're giving you in lab. So today you're going to have some sulfuric acid. Those are solutions. So they are homogeneous mixtures of two or more substances. So we talked about homogeneous way, way back when. What does it mean if it's homogeneous?
All the same.
It is all the same, and that's really important when we put out a solution. Because let's say I put out a solution and it's kind of like that chocolate in your coffee where maybe it's more concentrated on the bottom. The first person who goes up and they pour out some of the solution might get a different concentration than the next person, right? If it was not homogeneous. So anytime we have a solution for you, we must ensure that it is homogeneous. So that is actually the job of our lab tech. So he puts it on a hot plate, which also is a spin function. You might have noticed there were two knobs. One is a spin function, and we put in a magnetic spinner, and it spins it around and around, and it mixes it, and we like to think it mixes it perfectly to make a homogeneous mixture that is perfectly uniform throughout. So any questions about that homogeneous mixture? By the way, anybody thinking, oh my God, that would be the best job on earth, we do hire student lab assistants, and it doesn't pay wonderfully, but it looks great on your resume. So if you're interested in that, let me know and I will give you our lab tech's email. He's a really fun guy to work with. Some of you may know him from your last class, Karsten. He's a very fun guy, fellow Humboldt alumni. All right, so our homogeneous mixtures, they are 2 or more substances. So they can be 3 or 4, but most of the time they will only be 2, and in general chemistry, it is generally one of what we call a solute, like hydrochloric acid, sodium chloride, and the other one is usually water. So in general chemistry, we normally dissolve into water. When you get to organic chemistry, they have different solvents. All right, that said, solvent and solute. Solute is what you have less of. So if I was mixing sugar into water, sugar would be my solute. And again, if I was mixing sugar into water, water would be the solvent. So solvent is what you're putting it into, the solute is what is going in. So when we dissolve a solute in water, it is called an aqueous solution, and you've seen that aqueous term before in this class. So any questions on the difference between a solute and a solvent? All right, so here's just a more graphic picture of that, and obviously not drawn to scale. That is humongous, like bowling ball size of solute here. But the solute are going to be the particles getting dissolved. The solvent is what's doing the dissolving. But what we say in general is solute is what you have less of, solvent is what you have more of. And again, in general chemistry, we assume our solvent to be water if you aren't told anything else. Organic chemistry, they have to tell you what their solvent is. All right, and again, the solution is a homogeneous mixture of 2 or more substances. And what's getting cut off right down here. There we go. Is that when the solvent is water, we also refer to it as an aqueous or AQ solution. Questions on anything here for solutes or solvents? All right. So again, our solutions. This solution is made with 50 milliliters, which is 9.89 grams of hexane, and 2.25 grams of bromine. I want you to take a moment on your paper, try to identify which one is the solvent and which one is the solute. Remember, the solvent is what you have more of, the solute is what you have less of. All right, so which one is the solvent? I think I heard one person who's saying hexane. How about the rest of you? Yes, okay. You're just too tired. All right, so we definitely have more hexane. So does everyone agree the solvent to be hexane? All right, which means our solute is bromine, yes. Any questions on how we determine the solute and the solvent here? So just for fun, next time you're having dinner with your family or you're out with friends and they're drinking anything, you can be like, hey, do you know that's an aqueous solution and the solvent is water? They will think you're super cool. Educate the people at Starbucks. Did you know you're making aqueous solutions there? Do you know what your solvent is? They might be interested. I don't think they'll give you free coffee for it, but they might be interested. Or they might be like, hey, we're really busy. We've got lots of coffee to make. All right. So one of the most common ways we express our concentration is something called molarity, capital M. And this is how most of our bottles are marked in the lab. So molarity will be moles of solute over the total volume of the solution in liters. So it will always be moles over liters. Sort of a shorthanded way of writing this, which you will see me do quite a lot, is molarity, capital M, is moles over liters. And this is something you definitely need to know. So molarity is very important to us. So again, I will tell you with 100% certainty on exam 2, you will see molarity. All right, so questions on anything so far? calculate the molarity of a solution made by dissolving 23.4 grams of sodium sulfate in enough water to form 125 milliliters of solution. So we want to find our molarity. That means we need the moles of our solute over the total volume of solution. So if you had to guess, which one here is the solute? Sodium sulfate, yes. So I told you that water is generally our solvent. But here we are going to form 125 milliliters of total solution. So this will be our volume. So I'm going to have you calculate the moles of our sodium sulfate divided by the liters of solution. So what that means is you need to take your grams of sodium sulfate using the molar mass, turn that into moles, and take the milliliters, turn that into liters, and you'll divide them to get the molarity. So any questions about what we're going to do? All right, so go ahead and give that a try. Feel free to work with your neighbors. Let me know if you have questions. So 23.4 grams. All right, and next you had your molar mass, and what did y'all get for your molar mass?
142.05.
All right, so here in 142.05, did everybody get something similar? All right, and that is for 1 mole of Na2SO4. All right, so how many moles did y'all get?
165? Yeah.
All right, so I'm here in 0.165. Did everybody get something similar? All right, so questions on anything that we've done so far, finding the moles of our solute sodium sulfate? All right, so next up we're going to plug into our molarity equation. 0.165 moles of our sodium sulfate. All right, and it is 125 milliliters. What is that in liters? 0.125. Does anyone want to see me convert the milliliters to liters? Yes, no? Okay. So what is your molarity?
132.
All right, so I'm hearing 1.32. Did everybody get something similar? Okay. So your unit for this is capital M. Some people are asking if you needed to write the Na2SO4. It's nice, it's descriptive, but it is not required. So if I was looking for units, I would be looking for this capital M. And just a reminder, it does have to be capital N. In the very last chapter we're going to look at another concentration unit, and it will be called molality, lowercase m. And the difference is down here we'll have kilograms. So if you put lowercase m, I'm going to think molality, even though I know you guys don't know it yet. So it's very important that that's a capital M, and that I can read your handwriting that that is a big capital M. All right. How do our sig figs look? Yes? Good. All right, so it is 3 sig figs, because way back here in the problem, we had 3 sig figs for each one. And for our molar mass, we had 5, so we end up with 3 sig figs. So any questions on how we calculated molarity? Okay, so moving through this class, it's going to be really important that you can always calculate your molarity. And now when you go into the lab and you see a molarity written on the bottle, you can be like, dude, I know how to calculate you. Okay, questions on anything here? All right, so let's go ahead and take our break. So before you guys go, I want to give you your exams. Okay, so any questions on what we were doing before break? All right, so there is another way, and I would say probably a more common way of dealing with molarity, and that is as a conversion factor. So here we have 6 molar HCl, and it says how many moles of HCl are in 25.0 milliliters. Of that 6 molar HCl, But before we do the problem, I want to show you how to break apart molarity as a conversion factor. So what we know is that molarity is moles per liter. So if you have 6.0 molar, that is 6.0 moles per every 1 liter. So anytime you have a molarity given, it is a conversion factor. You put the number for the molarity with the moles, and you'll put a 1 with the liter. So with respect to the problem, we've talked about problems where you have 2 different numbers in there before, and my recommendation is always to start with the number that is not a conversion factor. So since molarity is a conversion factor, we are not going to start with that number. Instead, we're going to start right over here with our milliliters. But any questions on how I took that 6 molar and I broke it up into 6 moles per 1 liter, or why I'm calling molarity a conversion factor? Okay. So let's start with that 25 milliliters. And this is 25 milliliters of our solution. And SOLM is an abbreviation for solution. Alright, so I need to use the molarity conversion factor, moles per liter, but right now I'm in milliliters, so I need to convert to liters first. So milliliters on the bottom, liters on the top. And what's our conversion here? Milliliters, yes, 1,000 milliliters for 1 liter. Let me get this out of our way. All right, any questions about that conversion factor? All right, so on tests and quizzes, I always tell you to show all your work. However, milliliters to liters conversion or liters to milliliters, many of you are more comfortable doing it in your head. If so, this conversion right here, you're always welcome to do in your head. All right, from here, we're going to put in our molarity as a conversion factor. So we have liters on the bottom, moles on the top. The reason I have the liters on the bottom is because I had liters on the top before. And for every 1 liter, 6.0 moles. So any questions on how I set this up or how we're using molarity as a conversion factor? Okay, go ahead and take a moment and calculate out how many moles of HCl there would be in 25.0 milliliters of solution.
On a test, do you require us to use only dimensional analysis?
If you wanted to plug everything into here, you're welcome to. So if you wanted to plug in the liters on the bottom, the molarity on the left, and solve out for the moles on the top, you can. Is that what you were thinking, or a different way?
Yeah.
Yeah, no, that works, yeah. So just like a density formula, if you want to do density as mass over volume, yes. So what Eddie's asking is, do you have to do it this way, or could you just plug into the formula, and you guys are welcome to plug into that formula. As long as I can understand what you were doing. All right, so anybody get moles here? And you're proud of your moles? All right, did I hear 0.15? All right. See, I knew you were proud of your little moles. All right, so these are moles of HCl. All right, so questions on anything here? And again, in terms of units, the mole is the unit, but HCl is a nice descriptor, but what I'll be looking for in terms of units is that mole right there.
Would it be 0.150?
Oh, well actually no, because this is 2 sig figs right here. So let's talk about those sig figs. So here we have 3 sig figs. This one is exact, but your molarity does count, and this is 2 sig figs, and that's why we should end in 2 sig figs like so. All right, so other questions on this one? Okay, so this is another extremely common type of problem, and there is a high likelihood you might see this on a test or quiz. So make sure you're able to use molarity as a conversion factor, whether you do it by dimensional analysis or by using the formula. So questions on anything? All right, so here it says how many grams of sodium sulfate are required to make 0.350 liters of 0.500 molar sodium sulfate. So if you had to guess, which number do you think we're going to start with?
350.
Yes, this one right here. Because molarity is our conversion factor. So we're going to be starting with our liters, and molarity will allow us to convert it into moles. But we don't really want moles, we want grams. So then we're going to convert it into grams. How do we go from moles to grams? Molar mass, yes. All right, any questions on what we're going to be doing going from liters into grams? All right, so I want you to give this a try. Feel free to work with your neighbors and let me know if you have any questions. All right, what comes next? The conversion factor. So what goes on top?
Moles.
So moles will go on top. Liters on the bottom. How many moles? 0.5, yes. So 0.500 and 1 liter on the bottom. So any questions on how we did this right here or where we got that 0.500 from? Okay. Then we had one more step going from moles into grams. So for 1 mole, how many grams of sodium sulfate? I think I heard a 142.04 or 05? 05, okay. So something like, so 142.04 or 142.05? Yes? Okay. Any questions about how we set this one up? Okay, so what are y'all getting for your grams? 24.86. How about if we call that 24.9?
Yeah.
All right, and these are going to be grams of our solid Na2SO4. All right, questions about anything on how we did this one? Does this seem like the type of problem that could be doable? Should it rear its ugly head on an exam? Yeah. All right. So any questions on anything here? Actually saw a book. I actually got the audio book, and it's on about anxiety, but it's about how to master things that are difficult in your life. And the title of it, and I think it comes from some Buddhist saying, is first we make the beast beautiful. So first we consider it beautiful, then it's not as hard. I don't know if that actually works, but anyhow, just a thought as I called it an ugly beast. All right, the questions on anything here? All right, so next up is dilution. So dilution is used very commonly in industry, and it's also used very commonly in our stockroom. So when we purchase chemicals, we want to do it as economically as possible. That means buying the most concentrated form that we can, and then we dilute it down for you. So in our stockroom, which stays locked, we have concentrated acids, concentrated bases, not a place you want to be during an earthquake. But we dilute them down so that when you get them, most of the time they are dilute. Today is an exception. Today you're going to get to work with concentrated acids. But this is all about dilution. So how many milliliters of 3 molar sulfuric acid are needed to make 50 milliliters of 0.10 molar sulfuric acid? So there is a formula that will become your best friend in this class and those who going on to 1B. And it is M1V1 equals M2V2. So this is definitely a formula that you want to know. And this is actually a great formula Because while I wrote capital M for molarity, because that's what we use here in chemistry, if you're in biology, you might use a different concentration. Whatever unit you have, as long as it's on both sides, it is just fine. So molarity is fine on both sides. Volume could be in milliliters, could be in liters, could be in microliters, whatever it is. As long as it's on both sides, it is fine. So that's the wonderful part of this beautiful formula. All right, so now we need to identify what our M1, V1, M2, and V2 are going to be. So I like to think of the ones as before. The ones is before and the twos is after. So it says how many milliliters of the 3 molar sulfuric acid are needed. So that means I'm starting with that 3 molar sulfuric acid. So I'm going to call my M1 3 molar. Because this is what we're starting with. We're starting with our 3 molar sulfuric acid. And then down below is what we're going to make. So this is kind of the product. This is afterwards. And I'm going to use these as my M2 and V2. So M2, it's going to be 0.10 molar. That's what we want. And for the volume we want, it's going to be 50 milliliters like so. So any questions on how I set this up so far?
Does it matter if we have the H2SO4 with the, is that helpful to have it or no?
It's totally up to you. Here, everything is H2SO4. I'm more concerned with it when we have 2 different chemicals kind of at play.
Yeah.
But you're right, it's never a bad idea to label things more.
Okay.
All right, and so V1 I don't know, so I'm just going to put a little question mark in like so. So any questions on how we decided which one's M1, which one's M2, and so on? And again, for the volume, you're welcome to leave in milliliters. If you put V2 in milliliters, V1 comes out in milliliters as well. Some people are like, no, I must be in liters, and if you want to, you can, but I would just leave that in milliliters. All right, so now we're going to plug into our formula. M1 V1 equals M2 V2, with M1 being 3. I don't know my V1, so I'm going to go ahead and just write V1. M2, 0.10, and V2, 50.0 milliliters like so. All right, so any questions on how I set this one up? All right, go ahead and take a moment and solve out for V1. So 0.1 times 50 divided by 3, and just in case that is too small to see, I'm going to zoom in a little for you. Anyone get a value for V1? What was it?
1.7.
1.7. All right, so 1.7 milliliters like so. So any questions on that 1.7? Okay, so let's talk about what that one means. All right, so what this is saying is we need 1.7 milliliters of our original molarity, which is 3.0 molar sulfuric acid, to make this 50 milliliter solution of 0.1 molar. Now I have another question for you. We want to make 50 milliliters. We're going to use 1.7 milliliters of 3 molar. What else is going in there? How do we get from 1.7 to 50? What else did we add? Water. So when we're talking about a dilution, so think about it, you're making lemonade and for some reason it's too sweet. That would never happen to me. I love sugar, but let's say you're like, oh, this is too sweet. I need to dilute it. You are always going to add water. So in this class, when we talk about dilution, you have one chemical and water being added. So here we need 1.7 milliliters of 3 molar sulfuric acid and how many milliliters of water? What do you think? The rest and subtract. So go ahead and do that subtraction. How many milliliters of water do we need? I think I heard a 48.3, like so. Does it make sense why we need 48.3 milliliters of water? Yeah. Yes. Okay. So we need 1.7 milliliters of 3 molar sulfuric acid and 48.3 milliliters of water to make what we really want, which is 50 milliliters of 0.10 molar, like so. All right, so questions on anything that we did here when we broke it down and figured out how much water to add? All right, so there will be a lab not too long from now where we are going to ask you to prepare a solution, and you're going to have to figure out not only how much of the original solution, but also how much water you need to add to it to create your new solution. So always be aware that M1V1 gives you what you need of the solution, but you can find the water by subtraction. All right, so any questions on this or any questions on where we found that 48.3? Just for fun, if you go back and you can't quite remember how we got 48.3, it was 50 minus 1.7, like so. All right, questions on anything we did here with the M1V1 equals M2V2? All right, so here's another dilution problem. So here we have 10 milliliters of a 10.0 molar stock solution of NaOH, and it's going to be diluted to 150.0 milliliters. You're going to find the new concentration. You're using M1V1 equals M2V2. So go ahead and give this a try. What you're finding is going to be the new molarity M2. All right, so then you plugged everything in. 10 molar times 10 milliliters equals your M2 times 150.0 milliliters, like so. And what'd y'all come up with for your M2? All right, so 0.667, and the unit is capital M, or molarity. So any questions on how we're doing M1V1 equals M2V2? All right, so we will get a chance to do this in the lab, but this is another really important equation, M1V1 equals M2V2, that you definitely want to have down for our next exam. Questions on anything here?
And you call it molarity or molar? No, not molar.
We refer to it as molarity, but you can also refer to it as molar, so there's different parts of speech. So I could say this is a 0.667 molar solution, or the molarity is 0.667. Yeah, Andrew?
Do solutions actually exist in these like decimal points, or are they usually just like whole numbers?
Oh no, they definitely exist in a decimal point, and if memory serves, the solution you'll be creating in lab 8 is a 0.5 molar solution. Yes. So yeah, you are going to actually create, actually in a couple different labs, you're going to create solutions that are less than 1 molar. And if you're wondering, you can actually buy a solution in a 0.5 molar for sure, or a 0.1 molar. All right, so questions on anything here? Yep.
For the 6 figs on this one,
Yes.
I have 3, but I have 2 more.
So tell me about 2. How did you get 2?
From the 10.0, for the original.
So from this one right here,
Yeah, from, or both of them, yeah.
this one right here. So 10.0 is actually 3 sig figs, because zeros at the end, what we call the trailing zeros count.
I just found the middle one.
Oh, say one more thing.
Middle one before the decimals.
So anytime you have a number that's not 0, and then 0 is after zeros always count. So zeros count at the end, or they count in the middle if they're switched between two non-zeros. The only place they really don't count is out front. The 0.001, those zeros out front. All right, so other questions on this one? So in terms of dilution, I think probably the hardest thing about it is not M1 V1 equals M2 V2, so you probably already have some M1 V2 equals M2 V, M1 V1 equals M2 V2 fans in the audience. But I think the hardest thing is figuring out you're looking at a dilution problem. So the way you're going to figure it out is there's only one chemical and you're changing its concentration, which means you must be adding water. So again, only one chemical is involved. What people sometimes try to do is write a chemical reaction, but can you all see that there's no reaction that could be written because there's only one chemical? Just one chemical, you're changing the concentration. Same way as if you're making that lemonade and for some crazy reason it's too sugary, and you're going to dilute it to a less sugary, sounds terrible to me, but a more dilute, less sugary mixture. All right, as opposed to that, we're going to look at what we call solution stoichiometry. And so just to point out how this one is different than the one above, I can immediately identify that we have more than one chemical here. As soon as you can identify that you have more than one chemical, you cannot use the dilution formula. So that's a really common mistake because people love that formula M1V1 equals M2V2 so much because it is so easy. They will try to use it for a problem like this. But just looking at it and seeing that there are two chemicals, could you immediately identify that you cannot use the dilution formula here? Yes. Okay, so I'm going to put a big note on here. This is not a dilution. And the reason is because I can see at least two chemicals in there. So questions on that? Questions about why we can't treat this one as a dilution? Okay, so it says how much of the 0.115 molar Ki solution in liters is required to completely precipitate the lead in 0.104 liters of 0.225 molar lead nitrate. I know that sounds scary, we haven't gone over all of our reaction types, but all it is asking is how much Ki do we need to completely precipitate or to make all of this lead iodide. So the very first thing that I'm going to do is put my numbers right under the chemical reaction just so I know what we've got. So I'm going to say we got 0.115 molar Ki, and we have 0.225 molar of our lead nitrate, 0.104 liters of our lead nitrate. Here the deal is we want to use up the lead nitrate completely. We want to essentially match Ki for lead nitrate. So questions on anything that we've done so far? So we're going to do a lot of these solution stoichiometry problems. And these are going to be very similar to titration problems. Those of you who had intro chem, you did the titration problems. Later in this chapter, we're going to get a chance to do those. You'll get a chance to do them in lab. But I like to write the numbers right down here. And that way, it really reminds me that this problem is going to be so similar to those titration problems. So we have a quantity of Ki, we have a quantity of lead nitrate. The way I figure out where to start is I always start with a chemical we know more about. So I have more information over here, so I will be starting with the lead nitrate. So always start with a chemical you know more about. And then between molarity and liters, which one of these two numbers do you think we should start with? Liters, because molarity is a conversion factor, right? Okay, so my recommendation in this problem is always start with the volume of the chemical you know more about. Another way of saying that is go to the chemical you know more about, look for the one that is not a conversion factor, and that will always be their volume. So questions on anything there about why we're going to start with the liters? All right, so all the information we need is right here. And I'm going to start with 0.104 liters. Now, earlier, a few people had asked me about labeling things, and I said, since you're really talking about the same chemical throughout the problem, it's not as important. Here, it's extremely important because we've got two different chemicals. So this is 0.104 liters of lead nitrate. So again, for solution stoichiometry problems where you're converting between one chemical and another, it's really important you label things so things don't get mixed up. All right, so next up, I want to use molarity as a conversion factor. I know I'm going to need liters on the bottom, moles on the top, and both of these will be for the lead nitrate like so. All right, how many moles of lead nitrate should I put up there on the top? Yes, I'm hearing 0.225. So 0.225 moles for every 1 liter. So any questions on where that 0.225 came from? Just in case when you're going back later and you're like, wow, where did all that come from? It came from this right here. So questions on anything there? All right, so we have taken liters of lead nitrate and we have turned it into moles. But what we're trying to do is find the liters of Ki. So anytime you convert between one chemical and another, we need what? Yes, a ratio, the mole ratio from the balanced equation. All right, so on the bottom, I will have my moles of PbNO32. And on the top, actually, I'm going to move this to the next line just so we have a little more room. There we go. All right, so moles, PbNO32 on the bottom, and on the top, moles of Ki, like so. All right. How many moles of lead nitrate? 1. Does everyone agree on 1? We have an invisible 1 right up there. All right, how many moles of Ki? 2. Excellent. Any questions on where we're getting those numbers for the mole ratio from? Okay. Now we know our moles, and we really need to know our liters. So we have one more step. And so here I'm going to do moles of Ki, and on the top I will have liters of Ki. Now here again we're going to use our molarity. So how many moles of Ki? Yes, 0.115. And I know it looks different because it's on the bottom this time, but it follows the moles wherever they go. And I heard someone say 1 liter, and that is correct, 1 liter on the top. So any questions on how we set this up or about that 0.115 down here? So go ahead and take a moment and find out how many liters of Ki we need to fully react with the lead nitrate. Anyone come up with a value for liters of Ki? All right, so I'm hearing 0.407. Did everybody get something similar?
Yes.
All right. So, any questions on anything so far? All right. So let's talk about what we're doing here with these solution stoichiometry problems. So with these types of problems, you're given two pieces of information on one chemical, but only one on the other, and you are essentially trying to find the missing piece. So in this case, it's the volume that's missing, but it could have been the molarity that's missing. You were given three pieces of information and asked to find the fourth piece. So any questions on that you're given three pieces of information and asked to find that missing fourth piece? So my recommendation to you again, start with the chemical you know more about, and then start with the volume of that. And another way of saying that is start with the number that is not a conversion factor. Then you're going to follow it through just like we did, liters, then using your molarity, convert into moles, mole to mole ratio, and then molarity to get back to liters. So let me write this out the way we did our gram to gram conversion. I'm going to shrink this down. It'll be a little harder to see, but I want to put it all in the same line so you can get an idea of what we're doing. All right, so the very first thing that we did here is we went from our volume in liters, we went into moles, and you use the molarity given. So similar to the gram to gram conversion, but instead of using molar mass, you're using molarity. It allows you to convert between volume and moles. So that was our very first step. Our next step is going to be the same as what you did for the gram to gram conversion. Here we have a mole to mole conversion, also called the mole ratio. That's exactly what you're doing in your gram to gram conversions. You're using the numbers from the balanced chemical equation to convert between one chemical and another. And finally, third time's a charm. There we go. All right, finally, we are going from moles back into volume, in this case liters, and we are again using molarity. So it's the same three-step process, or I should say almost the same three-step process as you did with the gram to gram conversion, except instead of using molar mass to get from grams to moles, you're using molarity to go between volume and moles. Same mole to mole ratio, and now molarity again to get from moles into volume. All right, so questions on anything here? So questions about anything that we talked about today?
I have a question. So if we were looking for the molarity, not the volume.
Okay, good question. So let's do something like that. And later on we are going to do a few of these, but just as a little preview, let's say we had sulfuric acid and we were going to add NaOH to create water and sodium sulfate, something like so. And let's say that we had .5 molar of your NaOH, and let's say we have 25 milliliters of that. And let's say we use, 13 milliliters of our H2SO4, and what we're missing is the molarity. So something like so, yeah? Okay. So which of these three numbers would you all start with? But in terms of doing your dimension analysis, 25. Does everyone agree on that 25? Okay. Okay, so we'll start off in a similar way. So is it okay if I write this as 0.0250 liters, like so? Okay. Anyone want to see the conversion between milliliters and liters? Okay, so these are liters of NaOH. All right, if you had to guess, what do you think our next step is? Who is it?
Molarity.
Molarity, yes. How would you plug the molarity in?
Liters on the bottom.
So I heard liters on the bottom. And what goes on the top? Moles. All right, how many moles on the top? 0.500. All right, any questions on how we put that molarity in there? All right. Now, if you had to guess, what do you think comes next? Mole to mole ratio, excellent. So I'm going to put moles of NaOH on the bottom, and we will have the moles of H2SO4 on the top. How many moles of NaOH? 2. And how many moles of H2SO4? 1. Okay, now here is the part where I recommend doing it just slightly different than the other one. I'm going to recommend pausing right here and finding our moles. So let's take our 0.0250 times 0.5 divided by 2, and at this point we have 0.00625. And these will be moles of H2SO4. So we're still doing this a similar pattern, but I'm going to pause after the second one to get the moles, and that's because I like to use the molarity formula, which is molarity is moles over liters for the next part. So 0.00625 moles. And then what volume would y'all put at the bottom there?
0.
So 13 in liters, which would be, I think I heard 0.01300.
Yeah.
All right, so liters of H2SO4. So if I divide this, 0.013, it looks like we're going to get 0.48. I'm going to call that 481 molar, like so. So you're right, Jerry. I would do this one slightly different. You don't have to, though. There is another way, and the other way that some people like to do it is they add one more onto here, and they just say divide 1 over 0.01300 liters, like so. But I think it's less confusing to just total it and then do the molarity separate. And when we get to titration, we're going to do a ton of those. But does that sort of answer your question? Maybe gives you more than you were hoping for. All right. But any questions on anything here, the previous one, or what we talked about so far? Okay. And by the way, is it just me, or does it look like the screen is changing colors a little bit, like the bulb is going?
Yes.
It is? Okay, good. Okay. Before I put it in maintenance request, I don't want them to come in and be like, no, you're crazy. It's just fine. Okay. The colors look a little different than they did at the beginning. All right. Okay, so questions on anything that we've talked about so far? All right, so Liz planned to be in lab about 7:10, and as I said, you'll finish lab in enough time to go over your exam with me if you'd like, or to talk about the next homework assignment, or just to hang out and have a great time in chemistry class. All right, so I'll see you about 7:10 in lab. Oh, it's my computer that did it.